This is section 10.1, part 2. All right, so the last thing we did on the last recording was to come up with the standard form for the equation of an ellipse, which I'll repeat here so we have it to look at. The form of that's going to tell you that we have an ellipse is that it's a fraction plus a fraction equals 1. And those fractions have x squared and y squared in them. All right, and so the center is HK. R sub x is the x radius. That is how far we're moving in the x direction from the center, both left and right. And R sub y is the y radius. Again, how far you're moving up and down from the center. And the focal length C is a squared minus b squared, where a is the longer of the two. And I doubt you'll subtract that backwards, because if you did smaller number squared minus larger number squared, you get a negative number, and c squared equals a negative doesn't really make sense. So I'm not that worried about the order in which you subtract, because if you don't get a positive number, you need to reverse it. All right. So that is the standard equation for an ellipse. This is a pretty standard problem that I want to do here. Typically written in this order, the ax squared plus bxy plus ey squared, etc. Remember, the b is generally going to be 0. So notice there's no xy term in this problem, and there won't be for the vast majority of the problems that you encounter in this course. All right, so there we go. Now, we're supposed to find all of the information about the ellipse, the center, the vertices, the foci, and graph. And as I did before, the order in which I do this is not necessarily the order in which they state the tasks to do. So, by the way, you can tell this is an ellipse because the coefficients of x squared and y squared are the same sign. They're both positive, but they're different numbers. The coefficient of x squared is positive 4. The coefficient of y squared is positive 1. Since 1 and 4 are not the same, that makes it an ellipse. If they were the same, it would be a circle. All right, so we're going to need to complete the square to get the equation in that standard form written over there to the left side. So I'm going to suggest that what you do first is get all of the x's together, then get all the y's together, and then any constant, I would just go ahead and move it to the other side. So then the next thing I would suggest we do is to complete the square. Remember, to complete the square, the coefficient of x squared must be positive 1 inside of the parentheses. So I'm factoring off the 4. Then leave a blank space there for the number to complete the square. Since coefficient of y squared is already 1, I don't need to factor anything off, but I'm going to put it inside parentheses and leave a blank space there for completing the square. All right, so completing the square on x, half of negative 2 is negative 1. The square of negative 1 is 1. So I'm going to add 1 inside the parentheses. In reality, I just added 4 times 1 to the left side. So I'm going to add 4 times 1 to the right side. Then, completing the square on y, half of 4 is 2, 2 squared is 4, so I'm adding 4. In reality, I'm adding an understood 1 times 4, so I'm going to add 1 times 4 to the other side as well. Then factoring, that's going to be x minus 1 squared. And the other one will factor to be y plus 2 quantity squared. And the arithmetic on the right side gives me 16. Then, since the form is fraction plus fraction equals 1, to make that turn into 1, I'm going to divide everywhere by 16. So I'm dividing both sides of the equation by 16 to turn that into a 1 on the right. Luckily for us, and this won't always happen by the way, but luckily for us, 4 and 16 cancel nicely, leaving 4 in the denominator. There is no canceling required for the y fraction. It doesn't have a number in front of y plus 2 up there besides the understood 1, so don't need to do anything there. And just so that you know, in front of the x and in front of the y in the formula, in the x minus h squared and the y minus k squared, you cannot have a constant. So just in case this happens, this is just a what if kind of thing. If you had like, I don't know, 7 times x minus 3 squared. I'm just going to look at that one term. And to get the right side equal to 1, you had to divide by 25. Well, that 7 can't stay up there. And so what you need to realize is that that 7 divided by 25 is what you're doing, but it's going to end up being in the denominator. So if you think about it, you could rethink that as 25 divided by 7 in the denominator, which if you think about division of fractions, that's the same thing as times the reciprocal 7/25, which will take you back to there. That's a way you can check yourself. So thinking over here in the problem we were just working, I could have said that that's, for the first fraction, 16 divided by 4, which is how I got 4 under the x minus 1 squared. And the second one would be 16 divided by 1, which is 16 under the y plus 2 squared. All right, well, you won't see very many like that, but if you do, I want you to have the tools to deal with it. All right, so now that we have it in the standard form for the equation of an ellipse, you can easily look at the equation, identify the center. It's 1, negative 2. The x radius is the square root of 4, which is 2. And you're lucky, too, that these are nice, perfect squares. They don't have to be. Look at the example over there to the left. That would be the square root of 25/7 would be the radius length over there. Luckily, we don't have to do that, at least not yet. And the square root of 16 is 4. Okay, so I'm going to start plotting this. This is the way my mind goes at it. Once I have found all of the information I can from the equation itself, that is the center, the x radius, and the y radius, that's when I'm going to start plotting things so that I have a good handle on what's going to happen. All right, so the center is at 1, negative 2. The x radius is 2, so I'm going to move from the center 2 to the right and 2 to the left. The y radius is 4, which means I'm going to go from the center up 1, 2, 3, 4, and down 4. Now, in which direction did I move further? Was it left and right or up and down? Obviously, it's up and down because you went 4 in that direction instead of 2. Well, the direction you went further in, the points you get there are the vertices, not the other two. So they ask us to find the coordinates of the vertices. So I think now, right then, we're thinking about those points, and having plotted them, we know that we went further in the y direction. Those are the vertices, and the coordinates of those points are 1, the one that is up above is 1, 2, and the second one is 1, negative 6. Okay, so that's pretty easy to do. Okay, the foci are c away from the center. So I'm going to use the equation c squared equals a squared. A is the bigger one, so 4 squared minus 2 squared. Oops, well, I was going to write 2 squared, but I already squared the 4 to get 16, so I might as well square the 2 and write down 4. If I can make this thing work. Well, come on. There we go. So 4 squared minus 2 squared. So c squared is 12. And so c is the square root of 12, which simplifies to be 2 squared, so 3. So the foci are either left and right of the center that distance or up and down from the center that distance, because those 5 major points, center, vertices, and foci, are always collinear. Because we had to go up and down for the vertices, we have to go up and down for the foci. And notice, look at the vertices answer. The x-coordinate is the same as the center's x-coordinate because we went straight up or straight down. The thing that changed was the y-coordinate. So the same thing's going to happen for the foci. We're going to start at 1, negative 2, the center, and we're going to move up 2 square roots of 3. So add 2 square roots of 3 to the negative 2 and subtract 2 square roots of 3 from the negative 2. And those are the coordinates of the foci. Then to finish the graph, do your best with those 4 major points that are plotted to draw a curve, not a diamond. So nothing straight here, it's all supposed to be curved. Just do your best. It's hard to draw a perfect ellipse freehand, but do the best you can, and we're done with that example. And on these, make sure you reread the problem and that you've written down everything I asked you to write down. Are the coordinates of the center identified, and the vertices, and the foci, and the graph is there? Make sure all of those things are there. All right. Now, what's cool about the ellipse is, I don't know if you've been in places like this, but there are some museums that have a elliptical shaped roof in a particular room. And what's interesting is if you're standing at the focal, one of the 2 foci points, if anyone whispers from any other point in there, the sound reflects off of the ceiling and goes straight to the focus. And so you can hear someone whispering other places in the room if you're standing at the focus. It's a really kind of cool thing. Another thing about ellipses is the planets orbit the sun in elliptical orbits, and so that's a kind of a cool use of that. Now, some ellipses are going to be extremely elongated like this. Well, that wasn't very well drawn, but pretend. And others are going to be almost circular. And those are all ellipses. And so to measure just how oval the ellipse is, the ovalness of the ellipse, we have something called eccentricity. Eccentricity, E, and this is not E, the natural number E, this is just eccentricity, is always C over A. So for the problem we just did, C was 2 square roots of 3 over A, which was 4. Now that number is a relative number. I mean, so what? Square root of 3 over 2, what does that tell me? Well, if you think about the possibilities, in this case, for example, C and A are almost the same. C is way out here, and so is A. It's way out there. And so they're almost the same. And so C over A will be really close to 1 in that case. Whereas here in this one, C is really small and A is big. And so that C over A is really close to 0. In fact, every C value is, of course, a positive number, and it's obviously less than A. And because of that, at the extreme, one extreme, C over A would be close to 0. And on the other extreme, C over A would be close to 1. In fact, you can get from here to here by dividing everywhere by A. And so if you have an ellipse, the eccentricity will be a number between 0 and 1. And the closer that number is to 0, the closer it is to being circular. The closer that is to being 1, the more elongated that ellipse will be. Okay. On a following page, you'll see the eccentricities for several of the planets that are listed there. Notice how small they are. Those are all really pretty close to 0. Mercury is the least circular. It's the most elliptical of all of them. It's more elongated than any of the rest. The rest of them, being really close to 0, are almost circular. What if I asked you to find the area of an ellipse? Let's see if we can do that. The area formula for an ellipse. This is going to be the calculus we're doing in this section, by the way. So let's make this easy. Let's make this one centered at 0, 0. So x minus 0 is x squared, and y minus 0 is y squared. And let's make it go further in the x direction, just as we can. It doesn't really matter. If I were going to find the area of this ellipse, and this is A, and this is negative A. That's not a function. Obviously, it doesn't pass the vertical line test. So what I want to do is I want to look at just the top half of it and think of that as a function. And to find the area under that down to the x-axis is something that we know how to do from Calculus 1. And I'd have to double that number to get the area of the full ellipse. Okay, so that's what I want to do. So first of all, what is that function? What is the function that where y is equal to it? Gives me the top half of that hyperbola. Well, if I solve this equation for y, I will get y squared over b squared is equal to 1 minus x squared over a squared. Then if I were to multiply both sides by b squared, oops, getting ahead of myself. Multiply both sides by b squared. And I'm going to do something you may not readily see why I'm doing it, but couldn't I turn that 1 into a squared over a squared? So that this would be a squared minus x squared all over the common denominator a squared. Does that make sense? And I could write that as b squared over a squared times a squared minus x squared. Then I could solve that for y by taking the square root of both sides. Don't forget, when you take the square root, you put plus or minus in front of your answer. So the square root of that will be b over a times the square root of a squared minus x squared. Okay, and of course we only want the top half of that, so I want to keep that part. So let's see if we can write our integral. The area of the entire ellipse is going to be 2 times the integral of b over a times the square root of a squared minus x squared dx from negative a to positive a. Okay. So since you have a squared minus x squared under that radical, we're going to use trig substitution to integrate it. So I'm going to let u squared is x squared, so u is x, a squared is a squared, and so a will be a, and we'll replace u with a, because it's a squared minus x squared, we're going to replace that with a sine of theta. A sine of theta. Okay, so that makes this formula become 2 b over a, I pulled the b over a out in front, integral of the square root of a squared minus a sine of theta, which is what x is, quantity squared, so that'll be a squared sine squared theta. And there's a piece I forgot to do, so I better do it over here. And dx is a cosine theta d theta. So times a cosine theta d theta. Okay, so the a next to the cosine theta, if I were to bring that out in front, times 2b over a, that would cancel, leaving 2b. And if you factor out the a squared under the radical, you'll have a squared times the quantity 1 minus sine squared. The a already went out in front, so that would leave cosine theta d theta. Oh, and I forgot to figure the bounds. Let's see. The lower bound was when x is equal to the opposite of a, which is a sine of theta. That's what x is. And so if I divide both sides by a, I'll get negative 1 equals sine of theta. And that happens at wait a minute. I feel like I've made a mistake. Let me think about this. Okay. Well, I'm going to go forward with it and see what happens. It's not what I have in my notes, so that happens to be when theta is negative pi over 2. And for the other one, where x is a, which is a sine theta, which means 1 will equal sine of theta. That occurs when theta is pi over 2. So that means that my bounds are going to be from negative pi over 2 to pi over 2. Okay, so negative pi over 2 to pi over 2. I still feel like I've made a mistake someplace. I may have to go back and think about this a second and figure it out. Because it doesn't agree with what my notes say, but that's okay. Well, I'll figure it out. Okay, so if we take that a squared and do its square root separately from the rest of it, the square root of that is a, and 1 minus sine squared is cosine squared, and 1 minus sine squared being cosine squared means the square root of cosine squared will be just cosine theta times the other cosine theta that's already there. We'll make that cosine squared theta d theta. Okay. Why do I feel like I've made a mistake? Sorry, I'm trying to figure this out, and something looks wrong. I don't think I'm going to figure it out just by looking at it like this. So let me just keep going, and if I've made a mistake, then I'll have to come back and figure it out in a second. So, all right, so I'll pull the a out, and to integrate cosine squared, I'm going to use the identity where that's 1 plus cosine of double the angle. So double theta is 2 theta over 2 d theta. So if I pull that 2 out in front, I'll have AB, and then the integral of 1 is theta. The integral of cosine of 2 theta is 1/2 sine of 2 theta, evaluated from negative pi over 2 to pi over 2. And so it's going to be AB times pi over 2 plus, let's see, 2 theta is going to be pi. Sine of pi is 0, so that'll be 0. 1/2 times 0 is 0. Minus AB, negative pi over 2, plus 2 times negative pi over 2 is negative pi. The sine of negative pi is 0, so that'll be 0. 1/2 times 0 is 0. And so what we should get, if I hadn't made a mistake, is pi AB. And I think I did not make a mistake. I think I just did it differently last time I did it. I'll have AB times pi over 2 minus negative, so plus AB times pi over 2, which will be 2 of those. Pi over 2 is AB, so pi AB. Whew. Man. Okay, now you've probably heard before how you can have a rectangle, and all that requires is that both pairs of sides are parallel, and so far we have a parallelogram, and the angle at each corner is a right angle. That makes it a rectangle. So what is this? Well, it's a square. And it, of course, is a rectangle. It's a special rectangle where all four sides happen to be the same length. Well, actually, a circle is an ellipse. It's just one where the x radius is called r and the y radius is called r, and they're the same. And what's the area of an ellipse? Well, we just found that it was pi times a, the x radius, let's say, times b, the y radius, let's say, and the area of a circle, therefore, is pi r squared, which is consistent with the area formula for an ellipse, is pi times a times b. Now, that's quite the cool thing. So, let's move to example 4. So, example 4. Find an equation in standard form for the ellipse with vertices at 0, 3, and 8, 3. So you might be able to look at the coordinates and tell me where the center is without drawing a picture, which would be great. So, but I'm going to be a bit of a chicken and draw the picture. So vertex at 0, 3, another vertex at 8, 3. Where's the center? Well, obviously it's halfway in between, so it has to be at 4, 3. Okay, so that tells me right away that they told me it was an ellipse. And if you notice, the vertices are horizontally aligned, which means we're going further in the x direction because those are the vertices that are in the x direction from the center. So I'm going to start writing the equation. It is x minus the center's x coordinate, 4, quantity squared over. Now, do I know what the x radius is? How far is it from the center to a vertex? That's 4. That's the x radius. So down here will be 4 squared, x radius squared, plus y minus the y coordinate of the center, 3 squared, over the y radius squared equals 1. So actually I know everything I need to write this equation except for the value of b. So since this is the longer direction, this can be called a or r sub x in this problem. And the question is, what is b? Okay. Well, the only way we're going to be able to find that is if they give us some more information. So let's see, what's the other information they gave us? They told us that the eccentricity is 3/4. That means that the c over a reduces to 3/4. Well, we've already calculated that a is 4. And remember, eccentricity is c over a. So if a is 4, then what is c? Well, it has to be 3. And how will that help us find b? Well, for every ellipse, the equation c squared equals a squared minus b squared must be true. So 3 squared, 3 squared should equal 4 squared minus b squared. So that means that b squared should be 16 minus 9, which is 7. And actually that's as far as I want to go, because that's what goes under the y in that fraction is b squared. And so let me just do one little adjustment here. Instead of leaving that as 4 squared, I want to change it to 16, and we're done as soon as I change that to 16. And that's the equation that they requested that we find. Okay, now on to the hyperbola. A hyperbola is the set of all the points in a plane. And remember, the hyperbola has two branches because this is the one geometrically where the plane touches both cones. And we're only going to deal with the ones that open left and right or open up and down. They can open at different angles, but we're not going to deal with those for the most part. At any rate, these extreme points are the vertices on each branch of the hyperbola. That's a vertex and that's a vertex. This is a vertex and this is a vertex. These are not parabolas, by the way. They will remind you sort of two parabolas, but it's not the curvature of a parabola. So be very careful you don't think it's a parabola, although I sort of drew it as if it looked like one. When we get to graphing these with more clarity, you'll see that I didn't do a good job, and there is a way to make that better. Exactly halfway between the two vertices is the center, and the center is going to be HK. And the thing that makes it a hyperbola is that the distance, oh, and I forgot to say, and collinear with those 3 points are the foci. So let me put them in here. Let's pretend like the focus here is here and here. And again, they're kind of like inside of the curve, kind of like it was for the parabola. Those 5 points are collinear. The two vertices, the two foci in the center are collinear. And the definition of what makes it a hyperbola is for any point on either branch, it's going to have coordinates x comma y. And if you measure the distance from one focus, say this is focus 1, and so this would be distance 1. And the distance from that same point to the other focus, let's say that's focus 2, and this is distance 2. The difference between those two distances, which sometimes will be positive, sometimes negative, depending on which point it's closer to, which focus it's closer to. So to make it a distance, a positive number, we're going to take the absolute value of the difference between those two distances, and that will be a constant. And that's the way that we can derive the formula for the equation of the hyperbolas. So let's go about defining a few distances. We're going to say that the distance from the center to the vertex is again A. The distance from the center to the focus is again C. And there's some other distance that's not described yet, but it will be a vertical distance to some point out here. Let's just say it's right there. And another one over here. And I'm not going to tell you how you get those quite yet, but notice that that segment from yellow dot to yellow dot with the center at its is the midpoint between those two dots. That distance is perpendicular to the line that contains the two vertices, the two foci in the center. And we're going to call that distance that we move in that direction, the perpendicular direction, B. And as it turns out, if I were to draw something that's b in length, and then perpendicular to that, something that's a in length, the c would always exactly fit to make that a right triangle for every hyperbola. And so this would be c squared equals a squared plus b squared. Okay, so that's important. Okay, c squared is equal to a squared plus b squared. Alrighty, for hyperbolas. Contrast that with the similar equation for the ellipses, and remember that that was c squared equals a squared minus b squared for ellipses. It's important that you don't get these two equations mixed up with each other. All right, so as it turns out, if we were to derive the equation using the difference of these distances has to be a constant as the basis for it, you would get two equations. And this one I'm not going to have a single catch-all because it really makes a difference as to how you orient them. So let me finish what I'm going to say about the equation, and then I'll say again. So for this one, the one that looks like this, opens left and opens right, the one on the left, that's going to be x minus h over the x radius squared minus y minus k quantity squared over r sub y squared equals 1. And so that x radius here would be the a, and the y radius would be the b. Okay. Now the one that opens up and down, that one will be y minus k quantity squared over r sub y squared minus x minus h squared over r sub x squared equals 1. So whereas the equation of the ellipse was the sum of two fractions equals 1, this is the difference of two fractions equals 1. And what I was saying earlier is the order in which you subtract matters. And so if the fraction in front has x in it, that means that you're going to be going from the center in the x direction to get to all of the major things. I mean, moving left and right to get to the vertices and to the foci. If y is the fraction that's in front, what I call the positive fraction, you're going to have to move in the y direction from the center to get to all of your major things, your vertices and your foci. So here, it's not the size of r sub x compared to the size of r sub y that matters. Because remember, for an ellipse, a was always bigger than b. But for hyperbola, that doesn't have to be true. They could be a greater than b, a could be less than b, a can even be equal to b for a hyperbola. So what matters here is which fraction, what I call the positive fraction, what variable is in it. In the first case, x is in the positive fraction. And in the second case, y is in the positive fraction. And so those are equations that you need to learn. All right. Now, another thing that I haven't drawn yet, and the thing that's going to make the r sub y, the b, make a difference here, is that the hyperbolas are bounded by asymptotes. Okay, so let me draw one. Let's do an example really fast here. Let's do x minus 1 squared over 4 minus y plus 2 squared over 9 equals 1. Okay. And part of what I'm going to be doing is drawing the asymptotes and showing you how you get those. It's kind of my focus here. Okay, so the center is at h, which is with x, so 1, comma k, which is with y, negative 2. R sub x is the square root of 4, so it's 2. R sub y is the square root of 9, so it's 3. So when you go to graph this, let's see, the center is at 1, negative 2, so I'll give myself enough marks in either direction. I think I gave myself enough room. Okay, the center's at 1, negative 2, so plot that point. Then the x radius is 2, so from the center I'm going to move right 2 and left 2. The y radius is 3, so I'm going to move from the center up 1, 2, 3, and down 1, 2, 3. And so far this looks a whole lot like what we did for the ellipse, but with the minus between the fractions instead of plus. We're not drawing the ellipse that goes through those 4 points. Instead, we're going to draw a box that goes through those 4 points. So draw a box, a rectangle, such that each of those 4 points is the midpoint of the side of a rectangle. So that dot should be right in the middle of that side of the rectangle each time. Make sure these are visible. Okay. Then what I want you to do is draw the diagonals of that rectangle. Probably a whole lot better if I had a straight edge. If you want to use a straight edge here, you will have better result than I'm probably going to be able to get. But draw the diagonals of that rectangle. You might notice that they intersect, they meet at the center of the hyperbola. That's not a mistake, that always happens. So these are the asymptotes. The asymptotes, both of them, go through the center, HK. Okay. Now, an interesting thing I want you to see here is that the distance we went from the center up to that point is our change in y. And the distance we went from the center to that point is our change in x, what I called r sub y and r sub x. Well, if we wanted to write the equation of a line, aren't the change of y and the change of x essential to writing the equation of the line? Yeah, that's the slope of the line. So we went up r sub y and right r sub x, and so the slope of the line that goes up and to the right is, in this problem, 3 is our change in y over 2, which is our change in x. That's the slope of this line right here. Now the slope of the other line, this one right here, instead of going to the right r sub x, I'm still going to go up 3. Couldn't I go left 2 instead, which would make that slope negative 3/2? Well, notice they're the same numerical value, whereas one's positive because it goes up and to the right, the other one's got a negative slope because it goes down. So the slopes of the asymptotes are always going to be plus or minus, one positive, one negative, r sub y over r sub x. This is a generic statement right now. Oh, boy, that looks messy. Let me make that better looking. Okay, r sub y over r sub x. There we go. And if you use the point slope form of the equation of a line, you know that the equation of a line through point x sub 1, y sub 1 will be y minus y sub 1 with slope m equals m times x minus x sub 1. So in general, for all hyperbolas, the asymptotes will always pass through the center and will always have slope r sub y over r sub x and its opposite. So the asymptote equations will always be y minus k, because that's a point that they cross through, is the center, equals the slope. One of the slopes is positive, the other negative, and the slope value is r sub y over r sub x times x minus the x-coordinate of the point where they intersect, which is the center, so h. That's the equation of the asymptotes. So for this particular problem, the center being at 1, 2, this will be y plus 2, y minus negative 2 is y plus 2, equals plus or minus r sub y3 over r sub x2 times x minus 1. These are the asymptotic equations. Okay, now how does that help us graphing it? Well, since those are asymptotes, that means the curves approach those things, and you actually have two possibilities. You could go from the green dots and point up and down, or you could go from the red dots and point left and right. And so you have to look back at the original equation, and the decision is ruled by which fraction is in the positive position and what variable is used in it. In this case, it's the x that's in the positive fraction, so we're going to move in the x direction from the center to get to the vertex, which means that the red dots are the ones we use. So now just draw a curve that just gets closer and closer and closer to your asymptote. Okay? And so this one will open left and right. If the y had been in the positive fraction, it would have opened up and down. One thing I want you to be careful about that a lot of students make a mistake with is they're drawing, here's your asymptote, and you're drawing the curve and you're having to approach it, and you think, oh cool, I'm getting really closer and closer, and then you do this for some odd reason. Well, that makes you go away from the asymptote, which is bad. So please don't do that. That's wrong. Make sure it only gets closer to the asymptote, doesn't curl back around and go away from it again. Okay. So let's do an example that they have for us, example 5. We're supposed to sketch the hyperbola, sketch the graph of the hyperbola 4x squared minus y squared equals 16. Well, the form of the equation has to be fraction minus fraction equals 1. Oh, and by the way, in this ax squared plus bxy plus cy squared, etc. form equals 0, the way you can tell that it's a hyperbola when b is 0 is if the coefficients of x and y have opposite signs. So the coefficient of x squared is positive 4, the coefficient of y squared is negative 1, because they're opposite signs. That means this is a hyperbola. Okay, so, but it does have to equal 1, so I'm going to divide both sides by 16. For the x, that cancels to be 4 in the denominator. Y squared over 16 equals 1. So it's now in standard form for a hyperbola. We're ready to rock and roll. Okay, so the center is at 0, 0. The x radius is square root of 4, 2. The y radius is square root of 16, 4. Okay, so draw some marks on each of the axes. So the center is at 0, 0. The x radius is 2. So go from the center right 2 and left 2. The y radius is 4, so from the center go up 4 and down 4. And unlike the ellipse, those 4 points are used to draw a rectangle. So draw the rectangle so that the midpoints of the sides of the rectangle are those 4 dots that we created a moment ago. Then draw the diagonals of each rectangle. Then you have to choose whether they're going to open up or open down. Because the positive fraction contains x, that means they're going to open left and right. So kind of like the last one we did, this looks very similar to it. It's going to open left and right. Okay, so I'm going to need to stop and go to another file because I'm at the end of this one. So I'll see you in the next one.